Hi, and welcome to our presentation on learning direction fields for quad mesh generation. My name is Isaac, and this is joint work with Alexander Dielen, Max Leong, and Leif Kobbelt. Now, in the context of character modeling and animation, artists often use sculpting tools to create high-quality character models. The resulting triangle meshes are then carefully converted into quad meshes that can be more easily animated and subdivided as required. In particular, artists usually place additional edge loops around the surface regions that are likely to deform, such as the eyes and mouth of a human character. Unfortunately, this manual conversion is both labor-intensive and cumbersome, which is why a number of authors have proposed methods that can automatically quadrangulate a given triangle mesh. While these methods are able to reliably and robustly convert triangle meshes into quad meshes, they typically generate a mesh that looks like the one shown on the left, whereas most users would prefer a mesh that looks more like the one shown on the right. Now the question arises whether or not we can learn the structure of manually created quad meshes from a large shape collection using a neural network. However, applying a neural network to this task is not easy, since directly outputting a quad mesh would require the network to generate a valid mesh topology and satisfy global consistency requirements. Because of this, we propose a hybrid approach, where a neural network predicts the desired orientation and size of the quads, and then a classical quadrangulation algorithm handles the mesh generation step. Specifically, we base our approach on a parametrization-based quadrangulation method. These methods first identify a set of directional constraints that can be used to interpolate a smooth direction field, and then the resulting field is used to align a parametrization whose integer isolines are lifted back onto the mesh surface to extract a quad mesh. Our approach can be summarized as follows. Given an input triangle mesh, we use a neural network to infer a direction field that is defined on the input mesh. The direction field is then used to guide a parametrization-based quadrangulation method that then generates a quad mesh whose faces are aligned with the given direction field. More specifically, we train our network to output frame fields, which can be represented using two 2D vectors for every input triangle. This allows us to model non-orthogonal alignments as well as anisotropic quad sizes. In contrast, cross fields, which can be represented using a single vector per face, would limit us to orthogonal alignments and isotropic quad sizes. Our network follows a dual strategy that is based on the idea of combining both local and global shape information. To this end, we make use of a local network that processes surface patches and outputs a feature vector for every input triangle. Furthermore, we also employ a global network that operates on the entire input shape and outputs a feature vector that encodes global shape information. Finally, we also provide our network with a reference frame that describes the position and orientation of every input triangle. The motivation for this architecture is that the global network should enrich the features computed by the local network with contextual information. As a consequence, our network concatenates all of these feature vectors and then feeds the resulting vector into an MLP that outputs two 2D vectors for every input triangle. Now, the reference frame serves two purposes. On the one hand, it contains the barycenter of a given input triangle, which allows the network to extract relevant information from the global feature vector. On the other hand, the reference frame also contains a local coordinate system in which the two output directions should be expressed. The global network is based on the PointNet architecture and maps an input point cloud to a 1024-dimensional feature vector. In contrast, the local network is based on the spiral net architecture, which serializes the neighborhood of a given vertex or triangle using a sequence of neighboring vertices in order to aggregate local shape information. Specifically, the local network consists of 4 of these spiral layers and maps the neighborhood of each input triangle to 1024-dimensional feature vector. In order to train our proposed network, we need to design a suitable loss function. To this end, we have to consider the symmetrical nature of our target frame fields. Given the 2 ground truth vectors shown on the left, for example, the network should be able to output any of these vector pairs without incurring a loss. This is due to the fact that changing the sign of any output vector has no effect on the represented frame. In addition, we also have to consider the case where the order of these 2 vectors, which we illustrate using the colors red and blue, is swapped. This is due to the fact that the network cannot know the expected order of its outputs in advance. We can address this issue by making our loss invariant with respect to the sign changes. The second issue can be addressed by training the network using the minimum of 2 evaluations of our loss functions, where we swap the order of the predicted vectors u and v. To ensure that our loss function penalizes both direction and size errors in a balanced manner, we split our loss into a separate direction and size loss. Our direction loss is based on the von Mises distribution that approximates a normal distribution on a unit sphere. Specifically, the von Mises loss for a predicted angle theta and a target angle theta hat is obtained by computing 1 minus the von Mises density. As you can see on the right, this gives us a loss function with minima at multiples of 2 pi. Since our direction loss should be invariant with respect to the sign changes, or in other words, it should be invariant with respect to rotations of pi radians, we double the frequency of the cosine term. As illustrated on the right, this gives us a loss function with minima at multiple of pi. Using some trigonometry, we can adapt this loss to vector-based network outputs and targets. Since a frame field consists of 2 independent vectors for every triangle, we evaluate the resulting loss function once for each vector and sum up the results. For our size loss, we compute the absolute difference between the magnitude of the network predictions and ground truth targets. As an alternative, we also consider a relative size loss that expresses the same quantity relative to the magnitudes of the target vectors. Our experiments indicate that the relative size loss works slightly better than the absolute one. We believe that is due to the varying quad sizes in our dataset. We train our network on the dynamic Faust dataset, which contains 10 human subjects. Of these 10 subjects, we use 8 for training and validation and 2 for testing. The dataset was constructed by recording each subject in a variety of motions, such as jumping jacks and one-legged jumps. As a consequence, it contains 1 mesh for every recorded frame and more than 40,000 quad meshes in total. It should be noted that these meshes share their connectivity. That is to say, they were generated by registering a template quad mesh with a set of 3D scans. This, however, allows us to train our network on a manually designed quad mesh in a large variety of natural poses. Here we show a few examples that give you an impression of the variety of poses and body types contained in this dataset. To ensure that our network does not simply learn to align its outputs with the edges of the input mesh, we thoroughly remesh all meshes in our dataset. The ground truth directions for a given input triangle are obtained by projecting the barycenter of the respective triangle back onto the surface of the quad mesh, which allows us to derive the target vectors from the edges of the original quads. So here are 2 triangle meshes from our test set. And here are the quad meshes generated using the frame fields inferred by our network. Here are some close-ups that show a few more details. As can be seen, our meshes contain many semantic features, such as the edge loops around the eyes, mouth, and ears. In addition, the backs of our models are also clean and symmetrical, as demonstrated by the well-aligned singularities near the shoulder blades. However, looking at the two examples in the top right, we can see that the quality of our meshes decreases slightly under certain deformations, such as head tilts. In comparison with an existing field generation method, as for example the one employed by MIQ, we observe that our method generates quads that are much more similar to the ground truth. The perhaps most striking difference in overall fidelity can be observed in the faces of the depicted subjects, where our method manages to generate edge flows that are significantly more similar to those found in manually designed meshes. We can also measure this difference in mesh quality. For example, in this plot we show the angle errors incurred by our approach and MIQ with respect to our extracted ground truth fields, where higher bars on the left indicate a better result. As can be seen, our network generates directions that are significantly better aligned with the ground truth targets. A similar observation can be made for the sizes generated by our network. However, we would like to note that due to the lack of publicly available training data, our method is currently limited to human characters and therefore somewhat specialized. In contrast, MIQ is a general purpose method that was designed to handle many input types. Furthermore, MIQ does not actually generate a sizing field and instead relies on a uniformly chosen target edge length. To evaluate the generalization capabilities of our approach, we also generated quad meshes for the shapes in the Faust dataset. The Faust dataset contains multiple subjects not found in the larger dynamic Faust dataset. As can be seen, the results on this dataset are on par with those on our test set. But what about shapes that differ significantly from those in our training set? Here we show a quad mesh generated using our approach for a model of a young boy. As can be seen, the resulting quad mesh is of a similar quality as the ones generated for the shapes in the Faust dataset. Our method achieves this despite the fact that our training set does not contain any children. For a more stylized character with fairly exaggerated proportions, the quad mesh generated using our approach still resembles a mesh that an artist might produce. However, our method unfortunately generates a number of undesired singularity vertices around the mouth and nose, which can be attributed to the fact that the input mesh contains a modeled mouth cavity, unlike the shapes in our training set. For an even more unrealistic character, the quads on the hands, arms and legs and upper body are all reasonably well aligned. However, due to the substantially different proportions, the edge flow on the face is somewhat less pleasing. Finally, we also evaluated our approach on a mechanical component. Here, the inferred frame field is least likely to align with one a user might design. Nevertheless, in certain regions, the network does produce frames that are aligned with the principal curvature directions. This suggests that curvature information, among other shape properties, is taken into account. Of course, the network is not expected to outperform classical frame field generation algorithms on such mechanical parts, as it was trained exclusively on human characters. However, even on realistic human characters, our method occasionally fails to generate good results. For example, we sometimes observe frame fields that fail to account for head rotations. As a result, the edges of the generated quad meshes appear to be aligned with one of the global coordinate axes. Two particular bad examples where large parts of the generated faces are affected are shown here. Fortunately, this issue does not occur too often, and if it does occur, is largely contained to the heads of the generated meshes. In summary, classical field generation algorithms struggle to capture the structure desired by human experts, which may not be based on geometric features, but also on higher level information such as planned deformations or even aesthetic reasons. Neural networks offer a way to learn the structure from a large collection of shapes. Finally, we would like to note that our method is currently limited to a single object class, which is, of course, the class of realistic human characters. However, given suitable training data, we expect that our approach can be adapted to other input types as well. As a consequence, we believe that our work represents a first step towards the goal of automatically generating meshes that more closely resemble their manual created counterparts.